Friends, welcome to the tutorial series on network analysis made simple. During the previous tutorial titled Maximum Power Transfer Theorem Part 1, we derived the condition for maximum power transfer taking DC circuit and varying pure resistance load. In this tutorial, we take AC circuits and varying pure resistance load. In fact, when we say AC circuit, the varying load could also be complex. We shall take up this circuit during subsequent tutorial. Friends, consider the circuit shown in figure wherein the AC source voltage is Vs and the source impedance is complex and let Zs is equal to Rs plus Jxs. The load is varying pure resistance. As I said, the load could be complex in AC circuits. For example, consider a complex load consisting of say resistance and inductive reactance as shown. Reactance part could also be capacitive reactance. Now, if the load is complex, only resistance RL may vary or only inductive reactance component JXL may vary or both resistance and reactance part of the components may vary. In each of these three cases, the condition for maximum power transferred across the load will be different. So, we shall discuss these cases in the subsequent tutorial. Now, consider the varying pure resistance load RL. The strategy to find the condition for maximum power transfer to load is 1. Find the equation for IL in the circuit. 2. Find the modulus of current because the power is absorbed only in the resistance circuit element and we know power is equal to IL squared into RL watts. 3. Find the equation for power in the load. 4. Find dP by dRL and equate it to 0 and find the condition for maximum power transferred. So, from the figure, we see that the equation for the current I in the circuit is IL is equal to Vs divided by Rs plus RL plus Jxs and mod of IL is equal to Vs divided by square root of Rs plus RL whole square plus X square. Friends, how did we get this? Let me explain quickly for you to understand. Let us take a simple equation I is equal to 1 divided by A plus JB. By rationalizing it and solving it, we get I is equal to A minus JB divided by A square plus B square. Hope you understood this. Now, we can write I is equal to A divided by A square plus B square minus J into B divided by A square plus B square. Observe this equation. It is in I is equal to A minus JB form, wherein mod of I is equal to square root of A square plus B square. So, we get the mod of the current I is equal to square root of A square divided by A square plus B square whole square plus B square divided by A square plus B square whole square. By solving it, we get mod of I is equal to 1 divided by square root of A square plus B square. Hope you got it. But power absorbed in the load RL is P is equal to mod of IL squared into RL. By substituting for IL, we get P is equal to Vs squared divided by Rs plus RL whole square plus X squared into RL. Note that this part is mod of IL squared. Now, we have to find dP by dRL. So, dP by dRL is equal to Vs squared into d by dRL of RL divided by Rs plus RL whole square plus Xs square. Note Vs, Rs and Xs are constants. Therefore, using U by Phi form of differentiation, we get dP by dRL is equal to Vs squared into in the numerator, denominator into the differentiation of the numerator minus numerator into the differentiation of the denominator divided by denominator square. If we equate dp by drl to 0, we are left out with only this part because Vs squared and the denominator taken on the right hand side of equal to sign result in 0. Therefore, if dp by drl is equal to 0, we get rs plus rl whole square plus x square minus rl into 2 times rs plus rl is equal to 0. By solving it, we get RL is equal to square root of RS square plus X square, or RL is equal to mod of ZS. Once we know the value of RL when maximum power is transferred, we can find Pmax using Pmax is equal to mod of IL squared into RL. Friends, to emphasize the concepts we have learnt, let us solve an example to find the value of ZL when the maximum power is transferred across it. Also, we have to find the maximum power transferred. Observe the given network. Let the supply voltage be Vs, and Vs given is Vs is equal to 2 sin 2t. From the equation, we find that Vs max is equal to 2 volts and Vs RMS is equal to root 2 volts and omega is equal to 2 radians per second. Therefore, using these values, we get XL is equal to 1 ohm and its phasor form is J1 ohm. Similarly, XC is equal to 2 ohm and its phasor form is minus J2. Hope you know this. Incorporating these values, we get the circuit shown in figure B. Observe the circuit that the load branch is open. Also, two capacitive reactances of minus J2 ohm are in parallel. Hence, their equivalent is minus J1 ohm. Note, they are capacitive reactances and not the capacitances in farads. So, incorporating this reduction, the circuit drawn is shown in figure C. From the figure, we find that I is equal to root 2 divided by 1 plus J1 plus 1 minus J1, which will give us 1 divided by root 2 amperes. But V Thevenin is equal to I into bracket 1 minus J1, and by substituting the values, we get V Thevenin is equal to 1 angle minus 45 volts. To find Z Thevenin, by short circuiting the voltage source, we get figure A. We find two parallel connected branches, hence Z Thevenin is equal to 1 plus J1 into 1 minus J1 divided by 1 plus J1 plus 1 minus J1, which will give us Z Thevenin is equal to 1 ohm. So, RL is equal to mod of Z Thevenin, which will give us RL equal to 1 ohm. Using V Thevenin and Z Thevenin, the equivalent circuit across the load branch RL is shown in figure. From the figure, we find that IL is equal to V Thevenin divided by Z Thevenin plus RL. By substituting the values, we get IL is equal to 0.5 angle minus 45 amperes. Hence, mod of IL is equal to 0.5 amperes. So, P max is equal to mod IL squared into RL. By substituting the values, we get P max is equal to 0.25 watts. Friends, is it not simple? Friends, let us solve another simple example to find a maximum power transfer to load resistance RL in the circuit shown in figure 1. First, let us open the load branch as shown in figure 2 to find V Thevenin. We find that the circuit is reduced to a single loop network. So, I is equal to 4 angle 0 divided by 2 plus J2, which we get I is equal to 1.414 angle minus 45 amperes. But V Thevenin is equal to I into J2. By substituting the values, we get V Thevenin is equal to 2.828 angle 45 volts. To find Z Thevenin, let us short the voltage source to make it 0 as shown in figure 3. From the figure we find that 2 ohm and J2 are in parallel, hence Z Thevenin is equal to 2 into J2 divided by 2 plus J2, that is equal to 1.414 angle 45 ohm. For maximum power transfer, RL should be equal to mod of Z Thevenin. Hence, RL is equal to 1.414 ohm. Using Phi Thevenin and Z Thevenin, the Thevenin's equivalent circuit across the load branch drawn is shown in figure 4. We know that IL is equal to V Thevenin divided by Z Thevenin plus RL. Hence, IL is equal to 2.828 angle 45 divided by 1.414 angle 45 plus 1.414, which will give us 1.082 angle 22.5 amperes. So, mod IL is equal to 1.082 amperes. Hence, P max is equal to mod IL squared into RL. By substituting the values, we get P max is equal to 1.655 watts. Friends, is it not simple? Next, we shall solve another easy and typical problem to find RL for maximum power transfer, and also we shall find P max in the circuit shown in figure 1. As usual, to find VThevenin, let's open the load branch as shown in figure 2. Observe the figure, VThevenin is the node voltage as shown. By writing the Kirchhoff's nodal equation, we get VThevenin minus 12 angle 0 divided by 15 minus 2 angle 0 is equal to 0, from which we get VThevenin is equal to 42 angle 0 volts. To find Z Thevenin, let us short the voltage source and open the current source to force them to 0 as shown in figure 3. From the figure, we find that Z Thevenin is equal to 15 ohm. Note that the branch containing J2 ohm is open. So, for maximum power transferred across the load, RL should be equal to mod of Z Thevenin, and hence we get RL is equal to 15 ohm. Using V Thevenin and Z Thevenin, the Thevenin's equivalent circuit across the load branch drawn is shown in figure 4. From the figure, we know IL is equal to V Thevenin divided by Z Thevenin plus RL. By substituting the values, we get IL is equal to 1.4 angle 0 amperes. Hence, mod of IL is equal to 1.4 amperes. So, P max is equal to mod of IL squared into RL. By substituting the values, we get P max is equal to 29.4 watts. Friends, finally, let us solve another problem to find the maximum power in watts that can be transferred to the load resistance RL in the circuit shown in figure 1. As usual, let us open the load branch to find VThevenin as shown in figure 2. Observe the figure, you find that there are two parallel branches, one of 5 plus J5 and another of 10 plus 5 plus J5 across the current source of 5 angle 30 amperes. So, we can apply the parallel branch theorem or the current division theorem to find I2. Hence, I2 is equal to impedance of the other branch divided by sum of the two parallel branch impedances into the total current. So, by substituting the values, we get I2 is equal to 1.58 angle 48.43 amperes. But Thevenin is equal to I2 into 5 plus J5. By substituting the values of I2, we get Thevenin is equal to 11.18 angle 93.43 volts. To find Z Thevenin, let us open the current source to make it 0 as shown in figure 3. From the figure, we find that 2 two branch impedances, one of 10 plus 5 plus j5 and another of 5 plus j5 are in parallel. Therefore, by substituting the values, we get Z Thevenin is equal to 5 angle 36.87. But for maximum power transfer, RL should be equal to mod of Z Thevenin, hence RL is equal to 5 ohm. Using Thevenin and Thevenin, the Thevenin's equivalent circuit across the load branch drawn is shown in figure 4. From the figure, we find that IL is equal to Thevenin divided by Thevenin plus RL. By substituting the values, we get IL is equal to 5.89 angle 104.995 amperes. So, mod of IL is equal to 5.89 amperes. Hence, P max is equal to mod of IL squared into RL. By substituting the values, we get P max is equal to 173.46 watts. Friends, I am sure you have identified some of the skills to recognize the changes in the network connectivity when either the load branch is opened or sources are made zero. Thank you for watching this video.